Before we jump into acid-base equilibria, pH calculations, and buffers, it's important to understand the Bronsted-Lowry definition of acids and bases, and these are very fundamental for us understanding how they work. The fundamental definition of an acid is that they are proton donors. It seems strange at first, but think about a hydrogen atom, and we've got an electron, orbiting around a single proton. And when that hydrogen atom loses an electron, it becomes H plus or a hydrogen ion. And what is the creature composed of? It's just a proton. So a proton is the same thing as a hydrogen atom, a hydrogen ion or a proton, okay? So a hydronium ion is another polyatomic ion that shows up a lot, and that's H3O plus, okay? So we have a couple reactions here. Let's look at the first reaction. HCl aqueous reacts to form H plus and chloride. So here we can see the H plus being produced. It's being donated or split off the molecule. And so it's clear to see that that is an acid because it's given up its H plus. In the next reaction, it might be harder to see. We have HCl gas reacting with water to give this H3O plus thing, which we call the hydronium ion, and chloride. But if you look carefully at the HCl formula, we know that's an acid because on the very right we have chloride. And when HCl loses an H plus, it's going to have one less hydrogen in the formula and form chloride. So this is how we can identify the acid as being HCl. And that's a typical way that acids react in water. Now, acids also taste sour, whether we're talking about vinegar or lemons, for example. And also, acids turn litmus paper pink, and we're going to see that kind of chemical reaction in the lab. Bases have very similar definitions. They are defined as proton acceptors. So it doesn't matter what molecule we are talking about. If it reacts with a proton and it gains a proton in a chemical reaction, we classify that substance as a base. Now, hydroxide ions show up quite a bit when we're talking about bases, and this is a polyatomic ion with a -1 charge, and it's OH, okay? Now we have a couple different chemical reactions here. We have NH3 reacting with H plus to give NH4 plus. So here the ammonia molecule is acting as a base because it absorbs or adds to a proton, okay? This next reaction is harder to see once again because we have ammonia, which is a gas, reacting with hydronium ion to give ammonium and neutral water. It should be a liquid there, but neutral water, okay? Now in this case, ammonia is also the base because if you look at the formula, on the left we're going from NH3 gas, and then on the right we're going to NH4. So in order to go up in count by one hydrogen, it has to accept the proton, okay? So ammonia is a base also in that chemical reaction. Now bases taste bitter. If you ever had the occasion of getting a little bit of bar soap in your mouth, that tastes bitter because of the basic soap molecules. Bases also feel slippery. If you spilt bleach on your hands and then you went to wash your hands off, your hands feel very slimy because the base is actually reacting with the oils in your hand to make soap. Bases turn litmus paper blue, and we'll see that kind of chemical reaction in the lab as well. Now, a typical acid-base reaction looks like this. First of all, acids and bases are always going to be on the left side of your chemical reaction, and then conjugate stuff is going to be on the right side of the chemical reaction. Now, if you think about a coin, you have heads on one side and tails on the other side, and so it works similarly with acids and bases. If we have acid on one side of the chemical reaction, if we flip that, we're going to have a conjugate base on the other side. So acid becomes conjugate base, base becomes conjugate acid, okay? Just like heads becomes tails and tails becomes heads, all right? Now in this chemical reaction, we have ammonia, which is the base, and if you look at the nitrogen atom on the right side, you can see as part of ammonium, that's the conjugate acid. So our base has changed to become the conjugate acid. H3O plus is the acid, and remember it's losing that H plus in the chemical reaction, so that's why it changes from H3O plus to H2O. Our acid becomes the conjugate base. So let's do some practice problems writing conjugate acids. Now, they're going to have one more proton than the base. So a proton, remember, is comprised basically of two things. It's an H, and then it's a +1 charge. So we'll break this down into 2 steps. So let's write the conjugate acid of H2O. So step 1, we add an H to give us H3O. And then step 2 is add a +1 to our molecule, so it becomes H3O+. And so you can see that's hydronium ion. So hydronium ion is the conjugate acid of water. How about ammonia? So we got NH3, and again, let's do it in 2 steps. We want to add an H to give us NH4, and then we want to add a +1 charge to the formula there to give us NH4+. Okay? And how about this? Now here we're starting out with a negative charge, so watch out for your charges. So in 2 steps, we add H. So first of all, we add an H to it. Do not write HOH or OH2. That won't be accepted for the formula for H2O. Please have an understanding that when OH- picks up an H, it becomes H2O. And then what you need to do is add a +1 to the charge. So OH- becomes H2O-, and then when we change that charge, we add a +1, and so it becomes neutral. So just note how you have a -1, and then you add a +1 charge, so you get 0, and so that's why the formula of water is neutral here at the end, okay? So water is the conjugate acid of hydroxide ion. All right, let's now practice writing conjugate bases. Same kind of principle. These conjugate bases are going to have 1 less proton than the acid, okay? Which means 1 less hydrogen and 1 more -1 charge. Now I could have said 1 less plus charge, but it's easier just to say, just add a -1 to it, okay? So let's write the conjugate base of NH3. So first of all, remove an H. That's easy to do. We change the formula to NH2. And then, of course, we add a -1 charge, so it becomes NH2-. Okay, so NH2- is the conjugate base of ammonia. How about this molecule here? Here we're starting out with a plus charge, so watch out for that. First of all, we take away a hydrogen, so it becomes H2O+, and then we add a -1 charge. And please note that if you're starting out with a +1 charge and then you add a -1 charge, it just makes the molecule neutral, so you don't need to indicate the charge there. All right, how about this guy here? This formula is acetic acid, so we want to write the conjugate base of this. So we do 1 less hydrogen, so we remove a hydrogen from this molecule. It's always going to be the very first one on the very left, okay? And then step 2 is to add a -1 charge, so we add a negative charge, and that's acetate. And now some practice problems for you. So write the conjugate base of HSO3- and write the conjugate acid of NO3-.